everyone, Mr. J here again. Welcome back to Chem Talks. Today we are going to revisit empirical molecular formulas. Now we already talked about the difference between empirical molecular formulas. We talked about bonding, but today we're going to talk about how to determine the empirical or molecular compound when we're given a set of data. So let's go ahead and get started. If you remember from when we talked earlier about bonding, empirical formula is just the formula that is written with the whole number, smallest whole number ratio. For example, if we had magnesium and oxygen combined, Mg would be Mg2O2, right? The 2's canceled out, okay? So we want the lowest ratio with empirical formulas. We always use it for ionic compounds. Occasionally we'll use it for covalent compounds as well, but it's definitely always used for ionic compounds. So here's an example, NaCl, that's a 1-to-1 ratio, +1 -1. But if we have magnesium sulfate, okay, we have Mg, right, which is a +2, sulfate SO4 -2. When we crisscross, it'd be Mg2SO4 with the 2 in parentheses, but we reduce the 2, like charges cancel out. Okay. Here's another one, CH2O. That's a 1-to-2 ratio. A lot of our carbohydrates are based off of that. So if we have an unknown compound, okay, what we can use is our knowledge of the mole, which we've already talked about, and percent composition to determine the correct empirical formula. And once we know the empirical formula, then we can calculate the molecular formula based off that if we have a little data. Okay. Remember, we talked about this when we started moles, that in a chemical formula, the subscripts represents the moles of each number of moles of each element found in that particular compound. So if we have H2O, in that we have 2 moles of water and 2 moles of hydrogen and 1 mole of oxygen in 1 mole of water. So that's going to be important as we talk about empirical formulas. All right, so let's talk about how we can find these empirical formulas. First thing we need to do is we're given some data, maybe the number of grams of each element. So the first thing we have to do is convert each of those grams or whatever we're given of substances into moles. Once we know that, okay, we can do our next step. Now, if you're given percent composition, something made up of 25% carbon, 50% oxygen, 25% hydrogen, then what we're going to do is we're going to change those percents. We're going to make an assumption. We're going to assume that we have 100 grams. Okay. Well, if I have 25% carbon and I have 100 grams, it's 25 grams. Okay. Makes it easy to do. So doesn't matter with percent composition how much you have, the percent always stays the same. So we just assume it's 100 grams, which makes it a little bit easier to deal with. Okay, and then once we get in grams, then we can convert it back to moles. Okay. Your next step then is you're going to look at the number of moles you have of each compound and then divide each compound by whatever the smallest total moles are. This is going to give us our ratio for our subscripts. Hopefully, when we do this, we end up with a whole number. If we do, that becomes our subscripts. Now, if we end up with something like 1.5 or something, we're going to have to multiply by 2 because we never have 0.5 anythings for a subscript. So if we multiply 1 by 0.5 or by 2 to get it from 1.5 to 3, we got to multiply all the other ones. Okay. Common ones you'll see is 0.5, maybe 0.33. We have to multiply by 3. We'll do some practice with these in class. And then whatever answer you end up with, that becomes our subscript. Okay. And then we have to write them in the correct order. What's the correct order? Well, if it's an ionic compound, we know it's metal, non-metal. Okay. If you're not sure, probably my best piece of advice is write them down in the order that they give them to you. All right, so let's look at an example here. Let's say if I have 4.50 grams of a sample of cobalt reacts with 4.475 grams of chlorine to form a binary compound. Determine the empirical formula for this. Well, let's see. Cobalt's a metal, chlorine's a non-metal, so we're going to have an ionic. Okay. So first step, we're going to convert each of those to grams. So I'm going to convert my cobalt to grams and then my chlorine to grams. Okay. So I set up, right, grams, 1 mole is equal to molar mass. That gives me 0.07721 moles of cobalt. I'll do the same thing for chlorine. Okay. Now here's something that I suggest on this. Go ahead and take them out 4 decimal places on your answer. I know we've been around into 2, but for this it makes it a little bit easier, a little more accurate to do it. Next thing then I have to do is I have to divide each of these by the smallest. So what's our smallest? Well, 772. So I'm going to divide this by that number. Okay. And then I'm going to also divide chlorine by the same number, and I get 1 to 2. These now become our subscript. So I have CO1, which I'm not going to write the one, Cl2. So our formula is CoCl2. So pretty easy. Let's look at another one here. Here's a percent composition one. So a sample rubbing alcohol was contained 60% carbon, 13.4% hydrogen, and the remaining mass was due to oxygen. What's the empirical formula of rubbing alcohol? Okay. So first thing we're going to do is assume we have 100 grams. Then that 60% becomes 60 grams. The 13.4% of hydrogen becomes 13.4 grams. And then what do we do to find the oxygen? Well, we take 100 minus 60 minus 13.4, and we end up with the percent oxygen and convert that to grams. So let's look here. All right. So first thing we're going to do is convert our 60 grams of carbon. Okay. We're going to then take our 13.4 moles of hydrogen. We know 1 mole is 1.01 grams. Okay. Now it's just H. It's not by itself, so it's not diatomic. It comes out to 13.28, and 60 plus 13.4 gives us 73.4. So we subtract that for 100, and we end up with a 26.6% oxygen, which we convert to grams. We know 1 mole of oxygen is 16.00 grams, and we find out the moles. Now we can see our oxygen's clearly the smallest, so we're going to divide each of these by the 1.67. Okay. And when we do that, we're going to get our script. So 3.05, it's a couple hundredths, it's close enough to 3. 8 is easy, and then 1. So now what order? Well, probably easiest to do is put them in the order they give them. So it's going to be C3H8O. So there is our formula. If it's when you're doing your moles like we did over here with 3.05, it's within a couple hundredths, go ahead and round it. Okay, it's only when it's like 3.5 or 3.33 that we actually have to multiply. All right, try this one on your own. Okay, stop the video now, pause it, and then come back and we'll see how you did. All right, so this one we have lead, hydrogen, arsenic, and oxygen. So we have four different elements. Same thing, we're going to convert each of them to the moles. Okay, doesn't matter that we have 4, 5, 3, whatever. Same process. Now the smallest number is what? 0.00667. Well, that's going to be pretty easy for the first three. It's going to be 1, 1, 1, and then we end up with 4. Okay, so we said we're forming lead, hydrogen, arsenate. Okay, well that tells us lead goes first, hydrogen, and then arsenate. We can either look that poly up, or we can just kind of go by what we have. So it's going to be PbHAsO4 will be our formula. All right, let me have you try one more on your own. Okay, here's a percent one. Stop the video now, do it, and come back. All right, first step, change all your percents into grams. Assume we have 100 grams, okay, and then convert. Okay, so it's showing it a little different way right in it. So we end up with 1.887 moles of sodium, 0.9417 moles of carbon, and 2.83 moles of oxygen. Which one's our smallest? Well, that's going to be carbon. So we're going to divide everything by 0.9418. Okay, so we end up with 2 moles of sodium, 3 moles of oxygen, and 1 mole of carbon. So which order to put them in? Well, let's see. We got sodium and we have nonmetal, so this is probably going to be some sort of poly. So I'd probably do NaCO3, sodium carbonate. Okay, Na2CO3. Okay, so not too bad. This is pretty easy, as long as you can convert from grams to moles. All right, let's take the next step of this. And let's look at molecular formulas. Remember, we said molecular formulas is the formula for a covalent compound where they are sharing the electrons. Okay. Remember, molecular formula doesn't have to be the lowest ratio like we saw in empirical formulas. Okay. So the molecular formula, as we said, is a chemical formula for a molecule, which means covalent bonds are sharing electrons. Okay. And once again, the subscripts are going to represent the number of atoms, or in our case, the number of moles of each element in one molecule. Okay, when we're talking moles. And then, as we said, it doesn't have to be the lowest whole number ratio. Okay, here's an example. Here's ethane, glucose, here's lactose, dinitrogen trioxide. All these can be divided by 2 or 6. Okay, to be reduced down to empirical formula. But for molecular formulas, you don't have to do that. Okay, so what we're going to notice is that molecular formulas are simply a multiple of an empirical formula. We're going to take the subscripts of empirical and multiply it by some value to get the empirical, to get the molecular. So for example, CH, if we multiply it by 2, we get C2H2. Okay? Here is CH2. We multiply by 6. Here's glucose, C6H12. N2O2, we get N2O4. So these were just, we multiplied our subscripts by some value to get our molecular formula. Here's another one, NO2, we get N3O6, multiplying everything by 3. So all we really have to do is add one more step to our empirical. Okay? So the first thing we have to do to find molecular formula is find the empirical formula. Once we know the empirical formula, we can determine the molar mass of that. We know how to do that. Okay? And then generally what they're doing is they're going to give you the molar mass of your molecular formula. Okay? And you're going to take the molar mass of your molecular formula, divide it by the molar mass empirical, and get what we call multiplier. Okay? And what you're going to do with that multiplier is multiply the subscripts in the empirical formula by the multiplier, and that will give you your molecular formula. So you're going to take the molecular formula mass, your molar mass of your molecular formula, divide it by the molar mass of your empirical formula, and you get this value n. Okay? This is your multiplier. Then you're going to take that n and multiply it by all the subscripts of your empirical formula, and you'll end up with the molecular formula. So let's take a look at it. The empirical formula for ethylene is CH2. Find the molecular formula if its molecular mass or molar mass is 28.1 grams. So this is an easy one. We gave you the empirical formula already. So first step, we have to find the molar mass. We know how to do that. We've done that earlier. Add together and you get 14.03. Now you're going to take your molecular molar mass, divide it by your empirical formula mass, and get your multiplier. So your multiplier is 2. So what you're going to do now is take 2, multiply it by each of the subscripts up here, and you'll get your molar mass. So CH2, when we multiply by 2, comes C2H4. So pretty simple, just 2 additional steps. Dividing the molecular formula by empirical formula masses, and then multiplying out. All right, let me have you try this one on your own. Go ahead and pause the video. Once you've got the answer, go ahead and hit play and see how you did. Once again, don't cheat. Stop, please, please stop. Cheating's not going to help you on the test. Okay, so we figure out the molar mass. It has a molar mass of 88 grams. Okay, given the problem. Now we got to figure out the molar mass empirical formula, which we should have came up with 44.06 grams. So we're going to take 88 divided by 44, gives us a multiplier of 2. So we're going to multiply everything through by 2, and we get C4O2H8. So not too difficult. If you're having struggles, come see me. Okay, let's put it all together, both empirical and molecular. Problem might look something like this. Succinic acid is a substance produced by lichens. Lichens are a symbiotic relationship. We often see them on rocks. Chemical analysis indicates that it is composed of 40.68 carbon, 5.08% hydrogen, and 52.24% oxygen. It has a molar mass of 118.1 grams per mole. Determine the empirical formula and molecular formulas for succinic acid. Okay, so first thing we have to do, find the empirical formula, and then we can find molecular. So step 1, we're going to convert our percent to grams and then grams to moles. Okay. So just like we did, now we're going to divide it by the smallest molar value. Well, that's 3.39. So we're going to end up with a ratio of 1 to 1.5 to 1. Now look at this. We can't have 0.5. So what we're going to have to do is get this to whole number. Easiest way is to multiply that by 2. Okay. What I do to one, I have to do to the other as well. Okay, so multiply by 2. So I'm going to have 2 to 3 to 1. So C2H3O2, that's our empirical formula. Pretty easy. Step 2 now, we're going to find the molecular formula. First thing we need to do, they gave us the molar mass of the molecular formula. We need to find the molar mass of our empirical formula. Okay, we've done that already, comes up to 59.0 grams per mole. Divide the molar mass that they gave us of the molecular formula, which is 118.2. Divide that by 59.01. And once again, as our previous example, you're going to get a multiplier of 2. Now I'm going to multiply my empirical formula, all my subscripts, by 2, and I should end up with C4H6O4. Okay, not too hard. Let me have you try this one on your own. Go ahead and pause it. As always, please do pause. Come back to me when you are done. Okay, step 1. Find the empirical formula. They were in percentages, so we're going to assume 100 grams. That way all our percents become grams. Okay, convert to moles. All right, and our numbers down the bottom are just the weight of 1 mole of it. Okay, a little typo here. There should be 1 mole K there. And then we got our oxygen. Our smallest is going to be 1.2, so we're going to divide everybody by 1.2. You get a 1 to 1 to 2 ratio. So that's our empirical. K1, C1, O2. Okay, now we got to find the molar mass of that. That's pretty easy. Okay, we're going to take the molecular molar mass that they gave us in the problem, which was 166.22, divided by 83.02, and we get 2. That's our multiplier. So we're going to multiply each of these values right here by 2 and end up with K2, C2, O4. All right. As long as you go step by step, this is pretty easy. All right, guys. So today we talked about empirical and molecular formulas. We revisit them from when we talked about them bonding. Remember, empirical is the lowest ratio. Molecular we use for covalent compounds. Okay. If you have any questions on how to do these, see me before class, or we will go over this in class briefly as well. Until next time, guys, take care.